Now, one question is that you might wonder why I called it vanilla GAN. The reason that I called it vanilla GAN is because there are also other forms of GAN. Okay, so the most famous one, which is better than this one, is the Wasserstein GAN, which is the topic of the not this section, the section after. So this kind of GAN that we had is using essentially the most basic form of loss you can think of, the objective, right? And this is simply coming out of the discriminator classification problem. So the better one, as I told you, is Wasserstein GAN. And then the question is that you might say, what does Wasserstein GAN do different from this one? Well, this guy is essentially trying to do maximum likelihood implicitly. Or in other words, somehow tries to minimize the KL divergence between the data distribution and the model. But then Wasserstein GAN, once people understood that what they are doing here is essentially that one, they said why we should minimize KL when we do know that our model is actually working in the lower, like projecting lower dimensional latent to higher dimensional latent. This might sound a bit weird for you, but once we get into the next section, you're going to see it. Because like KL divergence is a kind of very good divergence, but this is going to be very strong. And because of that, sometimes it doesn't help you to converge to what you want. This makes everything numerically unstable. And then the idea in Wasserstein GAN was that just drop everything, use the Wasserstein distance instead. And that one is a smoother sort of divergence. So we're going to talk about that. No worries, the names might sound fancy, but they are at the end of the day very basic ideas. But if you want to understand how does this WGAN work, we really need to understand how we can interpret what we do here by the vanilla GAN as a kind of maximum likelihood estimation. Now, let's start with this one. This is the part that I want to show you that GAN is essentially doing maximum likelihood again, but this is doing it implicitly. It's not doing it any more explicitly because it does not have access directly to the likelihood. So now, let's just forget about this whole idea of likelihood first, and then we think generally about this question. So I gave you this idea, okay, if you just solve min-max, then you're somehow trying to fool as best as you could the discriminator, and that discriminator is the best discriminator you can think of, and because of this, essentially, you are doing fine, right? But this is just words, right? There is no concrete proof that we are really doing well, meaning that what comes out of the generator is going to look like a data sample, right? So if you want to really find that out, we need to somehow show this property. And the property is that if I go ahead and solve the min-max problem, so I'm going to get the best generator and best discriminator, that solution is going to, when I start from the latent distribution, is going to give me 1x, which is essentially distributed by a distribution which is very close to the data distribution. We should be able to show that. And you might think this is a very complicated task to do, but I'm going to show you this is actually not that complicated. We can simply do that, okay? In order to do this, let us first do a few idealization, and these are going to help us a lot when we want to do the analysis. When you look at GAN papers and GAN texts, they always start from this ideals case, right? But I didn't do that. I started from computational models because this is more sensible for us. So what I'm going to think from now on that my discriminator, which is d phi, I told you this is a neural network, this is able to realize any function, d. How can I realize any function by a neural network? If I want to really realize any possible function that I can think of, what should happen to the neural network? It should be infinitely deep, exactly, right? When I have a limited size neural network, then it's going to approximate many functions, right? But it's not necessarily showing all the possible functions. But if I go deeper and deeper and deeper, then it's going to get better and better in approximation. Now I'm thinking asymptotic. Like I assume like my neural network is infinitely large, right? So same thing I assume for my generator. So this essentially here what I'm saying that my networks are infinitely deep. Like, I can do whatever I want, right? So this is the ideal case. Now, in practice, you might say we don't have them. Well, if we just can show everything for this ideal case, then in practice, what we get is a kind of approximation of that, right? So it's better that we stick to the ideal case because ideal case is easier, okay? Another assumption that I'm going to consider is that my data set has infinitely large number of samples, okay? And what do I mean by that? I mean that when I compute that expectation hat, those estimate, they are exact, right? So if I have so many samples, then when I average over them, I'm essentially getting the expectation, right? So E hat is essentially E. I'm going to replace E hat with E. Again, in practice, I cannot do it, but if I have large enough number of samples, then I get a good approximation of that, right? So it's better that I stick to that one because that's going to make the life easier, okay? Everybody's cool? So generator, discriminator, and also data set are now idealized, meaning that everything is infinitely good, okay? Now, if I do that, then I can rewrite the objective function that I had in this form, right? So I do not have the objective function to be anymore a function of my parameters of the generator, my parameters of the discriminator, and my data set, where instead I actually have this form, right? In this form, it's a function of function g, right? It sounds a bit inconvenient, but you just need to think about any possible function you can ever think of, right? Any possible mapping from z to x is a g, right? And then you put it there, right? So it means that here g could be anything, right? Same for d. And d should be d could be again anything that is start from d-dimensional space and gives us some number between 0 and 1, okay? And now I replace also the expectation hat with the expectation themselves, okay? Everybody's cool? So you're happy with this expression now, right? So L of G and D. So it's essentially that loss that we had before, no idealized, right? Now, next thing, G, the generator, I told you is very general, right? So it means they can be any possible function. Now, I'm going to make this also soft assumption. I call it soft because it's not like 100% correct, but if my latent is large enough, then it's correct. So what is the idea here? I would say that this g functions, it could be any function. Then if I put one Gaussian z inside it, depending on what function I choose, I can realize one distribution at the output, right? Everybody's happy? Yeah? Everybody's cool? So this means that when I think about every possible g, eventually I am thinking about all possible output distribution, right? So if I change this function g, if I change the generator, the distribution of the output is going to change. Now, one thing that is here, just a side note, you don't need to confuse yourself if you don't get it. Just throw it away. But the point is that when z is very small and x is very large, then you cannot really have, if you play with all the functions, you cannot really realize all the distributions, right? Because you're getting from a smaller universe to a larger universe, right? But put that aside right now, okay? Because what we do know is that we are not targeting really the whole data space, right? You're targeting a manifold there. And the manifold is small enough that this argument here is pretty much okay, okay? So just to give you this idea that this is not mathematically 100% correct, but for the test that we are doing here, is fine. So everybody's cool? So if I can have any generator, it's somehow with some mild assumptions tell me that I can realize any distribution at the output, right? And now the thing that I'm going to do, I am going to write this L of G and D instead of that form in this form, and you just check and tell me if you find it okay. Let's do it together. This x here is GZ at the top, right? I told you that if I change G, then I'm essentially changing P hat, the distribution of the generator, right? Now, I replace that GZ by X, and then I do the expectation over P hat, right? This is exactly the same argument as the second one there, right? And the first argument is the one as before, right? Everybody's cool? If you don't get it, just let me know. I can explain it again. So you see what I'm doing here? So I'm replacing GZ, that G of Z here, this expression inside the discriminator. I'm replacing it with one X, the blue X here. And the point here is that this X is no more distributed with Q, is essentially distributed with the distribution at the output of the generator, right? And I say that this term is actually a function of P hat and D, because if I play with G, I am essentially playing with P hat, right? So if I can assume that I can realize any P hat by changing my generator, I am essentially trying to minimize, solve the min-max problem for this one. Everybody's cool? Questions on that? No question? Okay. It's a bit important to follow it. If you don't get it, just ask me. Okay, that sounds good. So if you got it clearly, then yeah, one point that I put here I forgot to mention is that this P hat term, this is exactly the guy that I told you we cannot compute, right? You remember when we wanted to just compute the output distribution, we couldn't necessarily do it, right? You remember that? That was the problem, that you didn't have the inverse and you could not compute that, right? But it doesn't mean that you cannot think of it existing, right? It exists, you don't have access to, right? And essentially, we don't need to have access to, we're going to see it, right? So the only way that we can play with P hat right now is to play with G, right? I'm going to change my generator, then the distribution is going to change. And what I hope, I want to just play with this G in a way that the output distribution is exactly my data distribution, right? This is what I'm looking for, right? Cool. Now let's write down the ideal GAN problem. So in the ideal GAN problem, I am essentially looking at this term, this objective, the likelihood, which is a function of the generator and discriminator. They are any possible function. And what I want to do, I want to solve the min-max problem, right? It means that I first look in the domain of all possible discriminators, and I find the one which is minimizing this, maximizing this likelihood. Once I found that, I put it inside this expression, so I'm going to put D star here, and then I'm only left with G, right? And then I try to find the G which minimizes that maximized likelihood, right? This is the min-max problem. But I told you if I play with G, it's equivalent to playing with P hat, right? So I could say that if I solve this problem explicitly, I am somehow implicitly solving this problem, right? So I am playing with my discriminator to maximize the likelihood. This is the inner loop. And then I am playing with my G to minimize that maximized likelihood, right? Which is equivalent to playing with my P hat to minimize that, right? Because once I play with G, eventually I'm playing with the P hat, right? Everybody's cool? And then the distribution that I see at the output of the generator, it is going to be the solution of this problem, P hat star, right? Everybody's clear? Question on that? No question? Okay. Yes? Okay, no question. Okay, so now, if I get my model solving this problem, I explicitly, as I told you, I'm solving this guy. This means that once I get my generator, this G star, whatever I get out of it is going to be distributed with this P hat star, right? This is the distribution given by the optimal generator, right? So anything that I get out of the optimal generator is distributed by P hat star. Everybody's cool? Question? No question? Okay. So now, the thing that I want to show you here is that if I solve this second implicit min-max problem, then this p hat star that you see here is going to be p, the data distribution. If I can show that, then I eventually say that when I explicitly solve the min-max problem, the output of the generator is looking like the data distribution, right? Sample of the data distribution. And in practice, what it means that if you use a computational GAN, then the output of the generator is approximating a sample from the data distribution, right? Of course, it's not getting exactly that guy, because we don't have access really to any G and D. We are limited with the models that we have. But when we have a deep enough model, then it's OK, right? OK, so let's try to do that. And if I want to do it, I want to solve this min-max problem here, OK? And if I want to, I solve it, but you're going to see that I cannot compute it. This is the whole problem that we have the deep models, right? But we can solve it. We can find out what is the solution, OK? Let's do it together. And the first thing that I want to do, I want first to solve the problem for the discriminator. So I want to solve the inner maximization. So at the discriminator, I want to see what is the optimizer, or the best D function that I can put here to maximize this expression with respect to D. To do that, I'm going to open up that likelihood term, OK? So this is the likelihood term. Let's do it together first to just make sure everything is clear. So we had this, OK, we already have the term here. Yes, the first line here. So the likelihood term is essentially the expectation over data distribution of log of the discriminator plus expectation over the generated distribution, right? Generative distribution here, log of 1 minus d, right? And now I assume that x is a continuous variable, so that expectation is essentially an integral, right? So I can write down whatever is inside the expectation, log d, times the distribution of x, px, this is p here, you see, p is showing up here, dx, so this is the first expectation. This is the second term, so log of 1 minus d times the distribution of the model, p hat, right? Again, we are not able to find out what is p hat in practice, right? But we can assume that it exists, right? And if I could have had access to this, I can put it here, right? Everybody's cool? OK. Now, next thing that I'm going to do, so when you look at the integrals, can I merge those two integrals? What is the data, the space that they are taking the integral over? X. This one is x, right? So if I have integral of f dx plus integral of g dx, can I write it down as the integral of f plus g dx? Right? OK. So I'm going to just merge them, right? So I'm going to merge them in this form. So it's going to be the integral, the expectation of log dp plus log 1 minus d times p hat, right? dx, right? Everybody's cool? OK. Now, if I want to find the optimal discriminator, I should forget about g. I can think of g to be fixed, meaning that I can think of p hat to be fixed. Then I need to find the function d, which is going to maximize this integral, right? Everybody's cool? OK. So the thing that I need to do, I need to find the function which is going to maximize L over all possible d. How can I do it? Any idea? If instead of a function, I had a variable, I wanted to find the variable which is maximizing an expression, what do I do usually? I take the derivative or gradient, and then I set it to 0, right? So I'm going to do the same thing here, right? So I'm going to compute the derivative of this loss with respect to function d, and then I set it equal to 0. OK? I want it to be 0. And if I can find that, given that I know this is a concave function, so as a side note, given that I know this is a concave function, then that optimal point, that optimal d is going to be found. The only question here is that what do I mean by computing the derivative with respect to a function? Yeah? That sounds a bit weird, right? And typically you have the Radon-Nikodym derivative definition, this notion, and this is going to help you to take derivative of one expression with respect to a function, but I don't want to open that up because that is out of the scope of this guy. The thing that I want to do here for you is to just do one super naive version of the same calculus here, okay? But that super naive is going to be very simple. That's going to give you the whole idea. So here, important attention. So it's a super simplified version of that calculus. I don't want you to do that, okay? But if you are interested, just check that term, and then you're going to see something about it. So what is the idea here? So I wanted to just maximize this term, right? This integral with respect to d. The thing that I'm going to do, I am going to focus on one particular point x right now, okay? I have one particular point x, and then I'm going to get in a vicinity around x, right? So if you think, for instance, the whole space of x is the 3D space, and this is the particular point x, I'm just taking one tiny ball around it, okay? Now, what I assume inside that ball, I assume that all of the terms inside the integral, p, p hat, d, all of them, are pretty much constant. They are not changing that much, yeah? Well, this is not possible, really, yeah? But this is going to somehow impose some smoothness conditions, right? But that aside, okay? So we assume somehow this is constant. If we assume that this is roughly constant in that point, it means that all of them, in any point inside this ball, I can somehow approximate or write the value of all of those functions with the value of the function at the point x, right? Okay, so I'm going to do that. So I'm going to write that L function that I had, which was the integral term. This expression is the one which I had under the integral. This is the integrand. So I'm going to compute it at x, and given that I assume that this is roughly the same everywhere inside in this vicinity of x, I'm going to take that and multiply it with the volume of that region. Huh? Everybody's cool? Right? Now, this is, when I'm computing the integral, I can approximate it as the value of the integral, value of the function at every single point multiplied with the tiny volume around it, right? And I just add all of them up, all in the space. This is going to be in the integral, right? Now, I can write down whatever is left out of this, vicinity. I can summarize them inside R. This is the remaining part. And we can think of that remaining part to be the same integral as we had before, but now we're taking out that vicinity of x, right? So that tiny part around x, we take it out. Yeah? We just approximate it with the first expression. Anything else, we just do the normal integral. Yeah? Well, this is hard to believe that you can do such an integral. It needs to have a bunch of constraints that you are able to do that. But, well, that aside, right? Assume that we can do it. Everybody's cool? Now, this remaining term, it does not depend on dx anymore, right? Because x was inside that tiny vx space that I just approximated everything there, right? It's out of there, out of the remaining part. So that R does not depend on d, the value of d at point x, right? Okay. Now, if I think of that, I want to find the d star, the optimal value for, or the optimal function. The thing that I can say that if I'm looking at any single point x, I can do the same decomposition that I showed you. Then I can go ahead and find the optimal value of dx. If you want, you can call it mu, as I show it in this slide. I'm going to find the optimal value of dx by computing the derivative with respect to dx at that point, right? So what does that mean, essentially? It means that I am looking at this d function, which is a continuous function, as a kind of piecewise vector. So I'm going to break it into tiny pieces, and at every single point, this function has a value, right? And I put it inside a vector. Now, if I increase the accuracy of this greeting, the vector is getting longer and longer. And eventually, I am approximating my function by an infinitely large vector, right? So this is the whole idea. So you think of your function to be an infinite vector. But to do that, you need to have lots of mathematical constraints satisfied. Okay? So moral of the story, we are thinking of this whole d function to be a kind of infinitely large vector. And the value of the function at every single point, well, is showing up inside the expression we have as we did in the previous slide, right? Now, if I want to compute the derivative, I'm going to compute the derivative with respect to every value inside this vector, or every value of the function at any point x. Meaning that I'm going to call this, for instance, dx value here that you see inside this expression, I'm going to call it mu, okay? And this mu is going to replace this guy. This mu is not showing up inside this r, right? Because r does not contain that part of the function, right? And now if I want to compute the optimal value of dx, I'm going to take the derivative of this guy with respect to mu, and I set it to 0. Okay? Okay, if I want to do that, essentially I need to compute this derivative with respect to mu, and I set it to 0. Now one question, what's going to be the derivative with respect to mu here at r? 0. The only guy that is going to show up is here, right? Which is eventually that I am taking the derivative of the integrand with respect to dx, assuming dx is a variable, right? This is essentially that calculus that I told you. But for it to work, there are mathematical prerequisites, as I told you. So don't think that it is that easy. But yeah, under some good conditions, we can do it. Moral of the story, so if I take the derivative with respect to mu or with respect to d, I'm going to end up with this expression. R is going to disappear. This v, again, I assume that this is fixed size. So I have a tiny ball, and I fix the size of that ball, right? So that is not important as well. The only thing that is important is the expression inside this brackets. And I need to set it to be 0, okay? So you can just set it easily to be 0 and find the optimal value of mu. And if you do that, you're going to end up with this expression. So the optimal value of mu, which we assume that this is going to be the optimal value of the function d at the point x, is going to be this expression. Px divided by px plus p hat x. Okay? Everybody's clear? Question on that? So I do know it's a bit of too much calculations I did for you, but I hope you get the idea. I mean, I could have been like even more naive, and I tell you just take the derivative of the integrand, set it 0, which some people do, but it is not correct. Okay? Everybody's cool? Okay. So, moral of the story, if you couldn't follow the details here, is not really important. The moral of the story here is that at the end of the day, the optimal d that we get is going to be p, the distribution of the data, divided by the sum of the distribution of data and distribution of the model. Okay? Now, one thing that you should pay attention here is that you eventually cannot compute d star. You cannot find the optimal discriminator, right? Because if you want to compute this, you need to know at every single point what is the data distribution, what is the model distribution. Data distribution, you don't have it. You eventually want to find it, right? And model distribution, we talked about it. We cannot compute it in this case, right? So it means that I would say if I could compute this d, and I could really minimize this optimization, that d should be of this form, right? But I cannot compute it. What do I do in practice with deep learning? What do I do? I approximate it. I think of D to be a neural network. I put it there. I minimize everything with respect to phi, right? And then once I do that, maximize it with respect to phi. And once I do that, that D-trained discriminator is going to approximate this function, right? It's not exactly. So you should pay attention. D star itself cannot be computed. What we do in practice is always we just put a deep model and we try to approximate it by training that deep model. Everybody's clear? Questions on that? No question? Okay, I know it was too tiring, but good parts are coming. Please stay tuned. Okay. So that's the optimal D. Okay, now what I want to do, I wanted to just solve min-max, right? The max problem is over because essentially I knew what is D star. So if I want to solve min-max, I can essentially replace D with the optimal D, D star, and now I'm going to remain by a minimization problem, right? I want to minimize L of G and D star with respect to G, right? We can go ahead and solve this explicitly, but it doesn't matter how we do it. At the end of the day, if we really solve this, what are we doing implicitly? We are solving, this problem, we are essentially minimizing this with respect to p hat, right? Instead of G replacing p hat, okay? But let me just write down first this L, the likelihood of G and D star. If you write down that guy, so instead of D star, I'm going to put P over P plus P hat, right? So the first term is going to be log of D, now it's D star here. The second term is 1 minus log of D, which is now D star, right? Now, the second term, can I simplify it? Yeah? What's going to be the second term? 1 minus that term is going to be P hat divided by P plus P hat, right? So I can write it down in this form, right? So I am essentially, instead of P, 1 minus this term, if I just simplify it, I can replace it with this term, right? P hat over P plus P hat, right? Now, every term here is essentially a function of P hat. I do know that I can control P hat only through G, right? But if I minimize the likelihood with respect to G, it's equivalent to say that I am implicitly minimizing it with respect to P hat, right? Everybody agrees? So at the end of the day, the distribution which is going to come out of the ideal generator, ideally trained by a GAN min-max problem, is going to be the solution of this one, right? The guy who is minimizing this term. Everybody's happy? Okay, cool. So if you are happy, now the interesting part is going to start. Okay, so if you didn't get the details, it's okay. Just take it from my side. If you're solving GAN, you're essentially getting or trying to make the output to look like P hat a star. Okay, this is going to be the distribution of the output of the generator if everything works perfectly. Okay. Now, let me define this guy. This is the average distribution. You have this guy inside the assignment 2. So in assignment 2, you play around with this and the Jensen-Shannon divergence. The average distribution is that I get P and P hat, and at every single point, I'm going to add them up and divide it by 2, right? So this guy is still a distribution. Everybody agrees? P is positive, P hat is positive. So P plus P hat is positive as well, right? Now if I integrate P plus P hat over X, it's going to be 1 plus 1 going to be 2, right? Since I have divided it by 2, I multiply it by half, it's going to be 1, right? So it means that this average distribution is still a distribution, right? Correct? Now, look at this expression. What is this guy at the denominator? 2 times average distribution, right? Here again, 2 times average distribution, right? Correct? So the thing that I can do, I can just replace that average distribution on the expression that I found. It means that P at a star is going to be a log of P over 2 times average distribution plus expectation over P hat log P hat 2 times average distribution, right? And I can take those 2 in denominator out, right? So I can write it down in this form. So I can keep P over average distribution, P hat over average distribution minus 2 log 2, right? And that 2 log 2 is not going to show up in the minimization, right? So I can forget about that one as well. Correct? So I have P hat a star to be the minimizer of this expression. Now, looking at this, one of these expressions, expectation of x distributed by p log of p divided by a. What is that? Does it remind you of something specific? KL divergence, great, right? That is KL between P and A, right? So if you remember, KL divergence between P and Q is the expectation with respect to the first guy, P, log of P divided by Q, right? Now the thing that I have here is log of P divided by A, and log of P hat divided by A. And both expectations are with respect to the nominator, right? So they are eventually KL divergence, right? Correct? So the thing is that I can replace this first guy to be KL, second guy to be KL. I don't really need the last guy. Does not depend on anything, right? So I can essentially write it down in this form, right? I have KL divergence, P and the average distribution, plus KL divergence, P hat, the output of the generator, KL average distribution, right? Okay? Everybody sees that? Now, this guy is a new divergence metric. This is what we call a Jensen-Shannon metric. Do you know Jensen? Who is Jensen? Jensen inequality. Do you know Shannon? You don't know Shannon. Claude Edward Shannon. You should know him if you are in my lecture. The one who established information theory. No, he's the one who just invented information theory. Channel capacity, if you know. Mutual information, this is the notion he proposed. Okay? Just search. It's not accepted. Someone in EC doesn't know Shannon. He is the godfather. Okay? Claude Edward Shannon, just search it. Okay? So, Jensen-Shannon divergence is this guy, okay? Which is not anything different from KL divergence, right? It's essentially a symmetrized form of KL divergence, right? Because KL divergence, when P and Q, if you change P and Q, is going to change, right? But here, if I change P and P hat, like I replace here P hat and I put here P, it's still going to be the same thing, right? So it's going to be symmetric. This is what we call it Jensen-Shannon divergence. So the divergence between P and P hat is going to look like this one, right? So P with its average, the KL divergence, plus P hat and its average using KL divergence, right? Now, you have this guy in assignment 2, and you play around with this guy in assignment 2 to feel comfortable with it, because this is, again, one of the cool divergence metrics, which is essentially based on KL divergence, nothing too much different. But this is going to have a bit of more nicer properties. One of them that you see immediately is symmetry. But there are also some sort of, somewhere it couldn't be defined where KL cannot be explicitly defined. So there are a bunch of properties like that. You have it in your assignment. This is a simple assignment, but you're going to get a feeling about that. But there is one key point which you are going to show in your assignment, and that is that if this guy is 0, if the Jensen-Shannon divergence is 0 between two distributions, and given that you assume those distributions are quite well defined, it means that they have non-zero values everywhere. Okay? This is not a big deal. If that thing is happening, then this is equivalent to say that the KL divergence is 0. So you can see it immediately here, right? If P and P hat are the same, KL is 0, right? When P and P hat is the same, what is the average of P and P hat? It's P itself, right? P equals by P hat, then average of P and P hat is P, right? And then it's going to be the KL between P and P 0. KL between P hat and P are the same. P hat and P hat, again, 0, right? So KL is 0, Jensen is 0, right? You can show that under mild conditions, the other way around is also correct. So Jensen-Shannon 0, KL 0, KL 0, Jensen-Shannon 0, right? And both of them are going to be 0, the minimum value possible, when both the distributions are the same, right? So moral of the story, what is happening when you are doing GAN training? You essentially are solving this problem. So you are minimizing the Jensen-Shannon divergence between the output distribution of your generator, which you cannot compute, but you are implicitly doing it, right? Using that min-max problem. You are minimizing that guy, and assuming everything is well defined, this is equivalent to minimizing the KL divergence. Now, before coming to GAN world, if you wanted to minimize the KL divergence, what would you do? Maximize the likelihood, right? So essentially, you are doing maximum likelihood, but since you don't have direct access to the likelihood, you are doing it implicitly. Everybody's clear? So I took you over all of this hard time this session to just end up with this conclusion that when you are training the GAN using min-max approach, the min-max optimization problem, you're essentially trying to make the output of your generator to look like data distribution, and you're exactly doing it by minimizing the KL, or the better version of it, the Jensen-Shannon one. Okay? That is the moral of the story. Moral of the story, GAN is doing maximum likelihood estimation, but implicitly, because it cannot do it explicitly. It does not have access to the likelihood. So everybody's clear? Questions? No question? So I do know that the details were not 100% like, say, charming details. I do understand that. And totally, this is like, it takes time to understand. I tried my best to break it as simple as possible. If you got the rough idea, that's from my side, that's enough. If you are interested to know more, if you are interested to know more, then you can just take a double check the lecture, and then you can take a look at the tutorial that I put in the further read, where Jan Goodfellow, the one who invented GAN, he has given a detailed discussion on that. Okay, so you can take a look at that one as well to get more details. But from my side, I totally understand if some parts are not clear at all. Okay, so it needs a bit of practice to get clear on that. So now some nice parts without having details. So this was like the data set, and at that time, 2014, they could just generate these samples, which was a kind of wow at that point of time. Okay, at that point of time, you could not see such outputs. Impossible, right? And this was why people were super excited about this model, because this is the first time we were getting really realistic samples, right? So now everything was good when it was proposed, but gradually came out a bunch of challenges about these models, okay? The key challenges about the model, the first one was the issue with training instability. So the training is not stable, meaning that when you are doing that min-max problem, then essentially because you need to wait for the inner loop to converge, then the outer loop to act, you can do it approximately, but that approximation is very sensitive. You can easily diverge, like the model does not converge when you are just doing the training. So this is one issue, and this is like extremely sensitive to hyperparameters. Like you change learning rate tiny bit, then it starts to diverge. Okay, so this was one of the challenges that people needed a lot of numerical tricks. One of them is the one which I told you, compute the loss for the generator to be, instead of log of 1 minus d, be minus log of d. So this was one of the tricks, and lots of other tricks, normalization and things like that to make it numerically stable. But it was very sensitive to that. This was one issue. The other issue was the idea, the problem that we call it mode collapse. And what is the idea of mode collapse? The idea is that sometimes, since you are doing everything numerically, then your generators start to generate some good samples. And those good samples are going to be given to the discriminator. It's going to get full, right? And since it's full, now it's going to send back no gradient, right? So the generator starts to learn that, okay, I only need to just give out those few samples. Side that is, I can just confuse the discriminator, right? So This means that your model, your whole training is going to converge, but once you use that generator, it's going to give you just few samples, right? All the time. It's not diverse enough. If you're really sampling from the cat image domain, you really want different cats, right? But it's going to give you just a few cat images, right? So this is one issue. So you're going to lack diversity. And one of the reasons that the people in the Wasserstein GAN work found out was that because of lots of details in those numerical, functional optimization that we are doing, it somehow makes, because we're doing everything implicitly, right? We are minimizing the KL implicitly. It somehow makes your distribution, the distribution that you learn, to fit the data distribution on one particular point, but being totally irrelevant in other points, right? But since it's picking there, then you are always getting sampled from there, right? So you're not getting the samples from the other cat domain. You're just focusing on a tiny part of the cat world, right? So this is the point that people saw there, and they concluded that the main issue is coming from the fact that we are using, or we are implicitly minimizing KL. And then they came up with a better idea. So that was the issue of the mode collapse, and the computational wise, as I told you, is very vulnerable to vanishing and exploding gradient because of that specific loss definition. Log is just ruining everything. Now, people were very excited about GAN, but the issue was it's good, but it's hard to make it work, till the other idea after 3 years came out was Wasserstein GAN. And the whole idea of Wasserstein GAN was that, okay, we know right now, we know that GAN is minimizing Jensen-Shannon divergence. Okay, maybe we can take that off. Instead of that, we put Wasserstein distance. Why we should put Wasserstein distance? Because that one is a smoother distance. And if you put that smoother distance, if your model is not exactly fitting to the data distribution, it's getting close to that better. Okay? And this is adding more stability to whole training. We're going to see it in the next section. Okay? Any questions on that? Was it worth it? Yes? Okay. So, yeah. Okay, see you then on Thursday with Wasserstein GAN.